So people are still coming in, but I'd like to welcome you to this bi-weekly climate seminar. One point, so I'm Julia Steinberger. I'm going to do the first part of the moderation, and then Tanos is going to take over. And today, because we've had a lot of discussions sort of spilling over the time of the seminar in the past, we've decided on a slightly different format to try to allow that discussion. So this is a trial run where we'll leave a bit more time after 1 p.m. So we've asked the speakers if they can stay around until 1:15 for the discussion. We don't have to go that long, but that's the idea, is to just have the time to do our discussion fully. I am now going to stop sharing the screen so I can see the bio and introduce Linda Mhalla. So we have two speakers today. The first one is Linda Mhalla. She is a postdoctoral researcher in the Department of Operations at the Haute École de Commerce de Lausanne at the University of Lausanne. She holds a PhD in statistics from the University of Geneva, and her research revolves around external dependencies, modeling, and causal inference with an emphasis on environmental and financial applications. And she's going to be talking about climate-related disasters and death toll. And so, Linda, if you would like to share your screen, and off we go.
Oh, I don't think it's on full screen mode. And do you have the same issue as before, or is it all right this time?
We're not seeing the full screen.
Oh, okay.
But maybe it's big enough to read. So
no, let's try again. And now?
Oh, perfect.
Yes, much better. Thank you.
Thank you.
Good. So yeah, I guess I can start then. Okay, so first of all, thanks, Julia, for the introduction, and thanks also for the invitation to present our recent work. And thanks to everyone for joining. Okay, so today I'll be talking about climate-related disasters and death toll, and this is recent work with Valérie Chavez de Moulin and Eric Jondeau, both from HEC Lausanne. So first of all, I'll present the database that we had at hand. So here we worked with the Emergency Events Database, EMDAT, which was launched by the Center for Research for Epidemiological Disasters. And actually, this is a database that reports the occurrence and the impact in terms of many factors of over 22,000 disasters. And the data that we had at hand were spanning the time period 1960 to 2019. And of course, we had different types of disasters. So we had biological disasters. Obvious example would be the current pandemic. We had environmental disasters, which they need no introduction, unfortunately, and technological ones. So here, an obvious example would be Chernobyl. So that's for the classification. And then for each disaster, we had different quantities in terms of impact. So we had the number of deaths, the number of affected people, the financial losses, and also the insured losses due to that disaster. And actually here, so first we will only focus on environmental disasters, and that would include meteorological ones, so heat, cold waves, storms, hydrological ones, so floods and landslides, and the climatological disasters, so we would have wildfires and droughts. So maybe here just one thing to mention is that in this analysis, actually we only focus on punctual events, meaning that the quantity of interest that you wanted to model were happening or occurring over a year. So actually we had to exclude droughts from this analysis, although the occurrence, for instance, might increase due to climate change. And this is actually because some droughts, they could last several years. So that's for the classification. And then in terms of impact, so although it would have been very interesting maybe to look at the financial losses, we actually here wanted to assess the societal impact of environmental disasters. So we only looked actually at the number of deaths due to those disasters. And of course, since we are looking at number of deaths, we had to normalize the data to take into account the fact that the population evolved in each country and differently, of course, and we normalized everything with respect to 2019. Okay, so regarding the location of the disaster, so we could have, for many types of disasters, we could have very accurate position or location of the disasters, but actually we decided to work with the World Bank classification, which classifies the world in these different 7 regions. And because actually it was much simpler than looking at country-wise data, otherwise we would have few data per country. So this means that the data and also the covariates that I will explain in a bit are aggregated regionally into these 7 categories or 7 regions. And also this means that the results that I will describe here will be reported regionally too. Oh, sorry. Yeah, okay. So that's for the data. Now, what was the aim actually of the study? So we were obviously interested in looking at the impact of climate change on 2 quantities. So first, on the frequency of disasters. So we obviously know that they will increase, but of course we are looking at different types of disasters. So we wanted to see the evolution of their frequency in terms of the type of disaster and also the location of the disasters. But also we wanted to assess the impact of climate change on the severity of these disasters in terms of their number of deaths. And here the disasters, as I mentioned before, are either water cycle related, so that would be floods, landslides, and storms, or temperature related, so that would be wildfire and heat and cold waves. And sorry, and more precisely here, we wanted to understand the historic dynamic between these quantities. So climate change and its dynamic with the frequency and the severity of the disasters. But more importantly here, we wanted to be able to make projections in the future for these quantities of interest. And to do that, we need to rely on adequate statistical models. But these models, so first they need to be accurate enough to explain the past, so explain the historical data that we have. And then more importantly here, they need to be quite simple to be able to make projections in the future. And then since we are talking here about climate change and we are in constantly evolving environment, this means that we are in non-stationary setting. So these statistical models need also to be non-stationary. And that non-stationarity, we actually here propose to capture that using a set of covariates. Oh, good Lord. Okay, so what are the 2 covariates that we will look at? So here we took the CO2 emissions per capita, and this would be a proxy for climate change. And we also used the GTB computed at purchasing power parity rates, which we assume to be a good proxy for disaster risk management. So of course, the relationship between these 2 is quite intuitive, since richer countries will be more willing to invest in implicit disaster insurances, also by providing quality infrastructure. But here also we can have an illustration so between of the association of the 2. So the top rows is the log of the number of deaths due to floods between 1960 and 1979. And the same data, but between 2000 and 2019. So you have the death on the left, we have the GDP per capita at PPP on the right. So we can see, we won't look into details in these maps or these regions because that would take a little bit more time. But the idea here is to see that there's a negative association between the 2, but more importantly is that this economic growth will affect the impact of climate disasters, but with different magnitudes across the regions. So this means that afterwards, when we look at the impact of the GDP or the CO2 on our quantities of interest, we also need to assess that impact regionally. So we need to take into account the spatial non-stationarity that we have. Okay, and I mentioned previously that one of the aims was also to be able to make projections for our quantities of interest, and that will be through the shared socioeconomic pathway scenarios that were elaborated by the IPCC for its 6th assessment report. So these are actually 5 words, 5 scenarios in which different socioeconomic choices have been made, and that lead to different mitigation and adaptation scenarios or challenges. So for instance, For each of the 5 scenarios, we have a projection for the population, for the economic growth, also the technological growth, the urbanization, CO2 emissions. So there are more quantities that were projected, but actually we will only focus on a few of them. So here we have just an idea of how these 5 SSPs, so shared socioeconomic pathways, are distributed, are represented. So actually here we will only look at 2 scenarios to illustrate our projections. The first one would be the most optimistic one. Let's start with the good one. The SSP1, which is the sustainable scenario, where we would have few challenges for both mitigation and adaptation, and we'll compare the projection under SSP1 with SSP3, which is the most pessimistic one, and which is kind of the business as usual scenario, where we have both high levels in both for both adaptation and mitigation. And more precisely, here we have, I'm really sorry, I think I'm having a lag when I click to the next slide and when it occurs. Okay, so here we have the projections for our covariates of interest under these 2 scenarios. And you can see that for the optimistic one, for instance, we have an increase in population, but quite moderate one, which is accompanied by a huge increase in the GDP. And of course, here the CO2 emissions are under control, whereas under SSP3, the CO2 emissions are exploding, and we also have a huge increase in population accompanied by a moderate increase in GDP. So these will be the covariates that will affect our models, and we'll be able, thanks to these projections, to project our quantities of interest in the future. Okay, so that's for the data, for the aim of the study. But of course, as I mentioned, we need statistical models. And here, looking, for instance, at the number of deaths, we can see that few disasters yield very large number of deaths. And this means that if you look at the distribution of the number of deaths, it will be quite skewed with quite a heavy tail. And when we talk about heavy tails, we usually talk about extreme value theory and extreme value models. And that's why I will go through a very quick crash course on Univariate extreme value theory. So the idea here, let's forget a bit about our data. The idea here, if we have realization of some random variable, here we have, for instance, these realization, we are interested here in the behavior of the large values of that random variable. So there's 2 venues here, either looking at what we call the block maxima approach, where we will define blocks of data and then only keep the maximum value. So that would be our red points here. So typically for environmental data, people look at annual blocks or even seasonal blocks. And then actually under certain regularity conditions, we can show that the limiting distribution of these red points will be a generalized extreme value distribution. And then there's a second venue where, again, we are interested in the behavior of the same large values of these realization of this random variable. And here, instead of putting blocks, we will only fix a high threshold. And we will assume that any observation that happened above that threshold is extreme, meaning that now we look at these red points here, and we can again prove that that in the limit, by taking higher and higher thresholds, the exceedance, so the difference between the red points and the threshold, are distributed according to generalized Pareto distribution. And actually in this work, we only focus on the generalized Pareto distribution to model the large observation actually of the number of deaths. And here, since our database is only about disasters, so actually every event is extreme here by definition. Yeah. Yeah, okay. Okay, and just to go through some mathematical notations here. So as I said, we have a random variable y, and if you take the exceedances conditional on the fact that we exceeded that threshold, then we model those exceedances in the limit using a generalized Pareto distribution GPD, which is a distribution that has 2 parameters, a scale parameter sigma and a shape parameter xi. So the shape parameter here in the GDP or even in the GEV is the most important parameter when we talk about univariate extreme value theory, because this is the parameter that will govern the behavior of your tail. So if it's positive, you'll have long and heavy tails. If it's equal to 0, you have some exponential decay in the tail. And if it's negative, you have a short tail or even an upper bound for your distribution. And here, just a quick illustration. So we get illustration. So again, we have our realizations, we have our distribution of the data. So here we can think of this as being the distribution, for instance, of the number of deaths. And then we only look at the right upper tail to model it using the GPD. And then this parameter xi will tell us how this tail behaves. Okay, and so here I didn't mention any details of how and why this theory holds, but the assumptions, the regularity also assumptions here include the fact that we need stationarity in our framework. So this means that the observation that happens, they happen according to the same distribution, for instance. But of course, in our data set, we don't have that, meaning that first we have temporal non-stationarity because we are actually looking at variables that are affected by climate change. And then we also have spatial non-stationarity. As we've seen before, the variables of interest have different behaviors according to the different regions. So that's why now we need actually to use a dynamic approach. But this is actually not that difficult because if we find a set of covariates that captures quite well the dynamic approach, that captures quite well the non-stationarity in the data, this means that if we condition on that set of covariates X, then we can go back to our classical framework. This is the GDP that we've seen before, but now the parameters of the GDP will depend on your covariates. And for instance, this is one example of the dependence between the covariates and the parameters through parametric regression. And that's what we will do here in our framework. So for instance, here, when we model the frequency and severity, we'll first focus on one given type of disaster. So we will do different modeling for each of the 6 types of disasters. And here first, we will model the number of disasters per year. So we should call it NTR, which is the number of disasters at a given year T and a given region, using a Poisson process. So for instance, this is a counting process. And here the intensity of the Poisson process will depend on the year and the region. And then for the number of deaths per disaster, that's what we will look at here. We will use the generalized Pareto distribution. As we said, this is because we have a heavy tail in our number of deaths. So the GDP here will have 2 parameters that are dependent on time and the region. And of course, from here, from an inferential time point of view, actually, it's more interesting to pool the data together from across all regions over all time, and then to use regression models to represent our 3 parameters. So lambda t is the mean of the Poisson process. It will be related to the covariates. This way, same for the shape parameter and the scale parameter of the GDP. And here the covariates are the ones that I mentioned before, so the CO2 emissions and the GDP, but also a regional dummy, because we've seen that we have a non-stationarity spatially. And of course, this means that the parameters will be regional and time dependent inherently. For inference, I won't also go into details, but here, since we are looking at simple models, as you've seen here, we have just a parametric regression model, so parametric relationship between the parameters and the covariates, very simple model. We will perform the inference by maximum likelihood, and the model selection will be performed by likelihood ratio tests. Okay, so let's see what we have for our data. So for the counting process, so the frequency of the data, so we found out that for all disaster types, the intensity parameter, so the mean of the process, depended significantly and positively on the CO2 emissions and also on the regions. So that was kind of expected. And then, yeah, okay, good. And then we were able to make projections. So here, for instance, we have projections for each of the 6 types of disasters. We have the annual number of disaster. So we have the current level between 2015 and 2019, and then we have projections for different years. So as you can see, we have an obvious increase, unfortunately, in the frequency of all disaster types. And actually, what's more striking here is for cold waves. and also heat waves, where, for instance, for cold waves, it's the share of Europe that will increase heavily here. And for instance, for storms, that would be for East Asia and Pacific. And this is under the projections under the worst case scenario, or the business as usual scenario. And if you look at the same picture, but under SSP1, so we can see that again, by 2040, we still have an increase in the frequency, but actually under this optimistic scenario, by 2100, we could reverse this trend of increase, and we could actually attain lower levels than the current ones. Okay, and now if you look at the severity, so the number of deaths per disaster, what you found out is that for most disaster types, the GDP, the GPD parameters were dependent significantly and negatively on the GDP, which was again quite intuitive. So it was only for heat wave, if I remember correctly, where the relationship was negative, but it wasn't significant. And then, so I'm not showing the projections for the number of deaths per disaster, although what you found out is that the number of deaths per disaster did decrease actually in both scenarios. And this is due to an increasing GDP in the projections. But what we wanted to see actually is the combination of both models. So if you look at the number of deaths annually, that would be this quantity S tilde, which would be the sum over, so the sum of the number of deaths per disaster, and the sum will go up to the number of disasters that we have per year. So here actually we'll combine the Poisson model and the GPD model, and then we'll combine also the effect of the CO2 and the GDP. And here are the projections. So this is under SSP3. So here by 2040, we have an increase actually in most, except for landslides. So in most disaster types, we have an increase in the annual number of deaths. But then of course, since we will have an increasing GDP, we will decrease that number of deaths. But this is under, of course, this does not hold for heat waves, unfortunately. But again, this is under SSP3. So this is like the worst case scenario. And if you now look at the best case scenario, the optimistic one, so actually we still, we see that, yes, we decrease the number of deaths annually, but actually the decrease is even more rapid here under this scenario. So actually, even I'm not showing it here, and it's not on the same scale than the figure before, but we found out that, for instance, the level at 2040 under SSP1 is 1.6 times lower than the level under SSP3. And actually this relationship is even like, it becomes 30 times lower by 2100. And this is, of course, because under SSP1, we have a huge increase in the GDP, and also the CO2 emissions are relatively under control. Okay, so just to sum up, and I'm a little bit over time. When we fitted our model, on historical data, we did confirm the link between CO2 emissions and the frequency of climate extremes, but you also have seen that there are discrepancies between the regions and also the different types of disasters. The same for the link between the GDP and the death toll. But then, based on those fitted models, we were able to make projections. So we've seen a striking increase in the frequency, but that's by 2040, and that's valid for both disasters. But we've seen that under the right societal choices, we could reverse that trend by 2100. And again, same for the annual death toll, where it also depends, so the projections or the evolution depends on the levels of challenges to mitigation and adaptations. And here, so I didn't discuss any uncertainties, computation of uncertainties, but we did do them. And actually they were quite small for the frequency and the severity, except for heat waves. And that's due to the 2003 heat wave, unfortunately. And finally, just a quick word about the limitations. Of course, there are some of them. So the first one is we assumed that the effect of covariates on frequency and severity were the same, meaning that the relationship between the CO2 and the frequency is the same whether we're in 1960 or 2019. This could be improved, but actually here we wanted to keep.
Linda, we should just wrap up. Oh, just because
Yeah.
we should wrap up, so maybe we can discuss that in the discussion part.
Okay, that was the last slide then. So thanks.
Okay, thank you so much. Eric Jondeau is a full professor of finance at HEC Lausanne at UNIL and with the Swiss Finance Institute faculty member. He's the director of the Center for Risk Management and at Lausanne since 2012. He also is coordinator of the Systemic Risks and Sustainability platform of E4S. His main research interests are sustainability finance, systemic risks, and financial econometrics. And he is going to talk to us about how to decarbonize a portfolio. And thank you so much, Eric.
Thank you very much for this introduction. So I'm going to talk about finance. Just one thing to mention. So it's a joint work with people from the Bank of International Settlement. So it's not a bank. Huh? So there is no conflict of interest between the kind of people I worked with and the topic. So they are regulators, not banks. So the question today for my presentation is about how finance can help the transition, and in particular, how we can reduce the carbon contribution of large investors. So just one word to start with. Usually when we talk about the impact of climate change, there are at least two different meanings. One is the implied physical risk. Essentially, that's what Linda presented. That's the economic cost and financial losses that could be implied or would be implied by climate change. What I'm going to talk about is slightly different. That's what we call transition risk. And transition risk is the risks that are associated with the uncertainty in the financial impact of a rapid low carbon transition. So probably you are probably less optimistic than people in finance. So I'm not sure I would expect a rapid or a too rapid transition to low carbon, but that's what people in finance are also concerned about. And in particular, if there are some political changes toward a faster low carbon transition, that there would be some impact on asset managers and in particular on the value of portfolios. And that's typically the kind of thing we want to also deal with. So there are two, just to continue with the two scenarios from Linda, the SSP1 and SSP3. So SSP3, if we are in a business as usual scenario, there will be high physical risk, but relatively low transition risk. So, no stranded assets, no loss of value for coal mines and so on and so forth. But if we go for the SSP1 scenario, which is the optimistic one, sustainable scenario, that would be the other way around, right? I mean, the physical risk would be much lower, but there would be some high risk from the transition point of view. Okay, so just because we would have to close some coal mines, we would reduce the extraction from oil and so on and so forth, and that would have an impact on portfolios. Portfolios, it's okay, that's finance, but that's also our pensions. So there would be an impact on from a financial point of view. So that's the kind of question I want to ask in this discussion. Okay, so so the purpose is precisely to deal about how we could in a finance environment, how we can change things if there is any way to do this. So the starting point is really all the discussions we had in last year around the COP26 and several countries. I mean, actually quite a lot of countries have committed to reduce their carbon emission. It's still open. It's still an open question how they're going to do this, but there is this commitment, and it's not only about states. I mean, it's also about agents, economic agents. So it includes banks and asset managers and firms and so on and so forth. So all these institutions are supposed to do something at some point to reduce the emissions. And the question I'm interested in, because I'm doing finance, I'm interested in climate change. So the question is, okay, so what can the financial system do from the transition perspective? So there are two things essentially that the financial system can do. The first thing is banks can stop lending to highly polluting firms. Okay, so it's not the road they decided to follow for the time being, but this is one option, and probably at some point they will be forced to do this. The second thing is asset managers can stop investing in highly polluting fields. Okay, and that's something we can, in some sense, more easily check and investigate. So I'm going to focus on this second part. So what about this way to reduce the emissions of a portfolio? There are essentially two ways that people are considering. One way is to exclude firms that pollute a lot, and the other way is to try to convince these firms to change. Okay, so that's the difference between the exclusion from a portfolio and engagement. So what about these two strategies? So one way we can follow to try to reduce the carbon emission in society is to change the composition of the portfolio, reduce the number of firms that are polluting a lot. Okay, so in this case we are targeting the highly polluting firms. Typically, that's what the Norwegian Wealth Fund is doing. And they do this on a regular basis, and they exclude coal mines and so on and so forth. Another way is not to change the composition of the portfolio and try to convince the companies to change their carbon policy, so to reduce their emission. That's what large asset managers like BlackRock, I guess this is a asset management company, and that's what they claim they do. Okay, and the third way is to do nothing, and that's what the Swiss National Bank says. They don't care, and they don't do anything about this from this point of view. So what about these two different approaches, and why don't they want to exclude firms? Most of the asset managers, they don't want to exclude. They want to keep the shares in the highly polluting firm. And one reason is they don't want to be too far from their benchmark. So they are evaluated according to these benchmarks. They don't want to move away from the benchmark. And the second thing is what they claim is they want to have an impact on the firm. They want to convince the firm. Most of the time, what does it mean? It means that if there is a resolution proposed at the annual General Assembly, they will vote yes, just to improve the reporting of the firm. So essentially, the impact is quite limited. What about the exclusion strategy? So we start excluding firms that pollute a lot. So quite obviously, it's going to have a huge impact on the fund, so on the asset manager carbon footprint. This is for sure. It's going to probably increase slightly the cost of financing of the polluting firm, which is good. But unfortunately, it's going to have a relatively limited impact on society. Why? Because if you sell the shares that you hold in your portfolio, it's going to be bought by somebody else. Okay, and probably at the end of the day, it's going to be bought by hedge fund managers, and it's not going to improve the society emissions. Still, I'm going to focus on this exclusion strategy, and the idea is to build a portfolio that will be consistent with Paris Agreement, which means can we define a trajectory for a portfolio and reduce the emissions of a portfolio that will be compatible with, let's say, 1.5 degree increase or 2 degree increase. So the key thing for investors and asset managers is they want to stay as close as possible to their benchmark, because again, that's the way they are going to be evaluated. Okay, so that's the question is, can we do this? The answer is yes, we can do this. We have to follow some rules and try to implement this rule in a smart way, but that's something we can do. So what I'm going to argue in the next slides is we can do this provided we do it in a smart way. So the smart way means we need to exclude the most polluting firms and reinvest in the same region and in the same sector as these highly polluting firms. In other words, if you want to exclude a firm that is producing coal or that is producing electricity using coal, you need to reinvest the funds into, let's say, companies producing solar panels. Okay, so it's still the same kind of company, but it's doing, it's producing in a clean way. Once we do this, and I will try to convince you that this is one smart way to proceed, then you need to follow this trajectory until you decarbonize your portfolio, and it takes time, right? So I mean, you cannot reduce to zero the emissions, the carbon footprint of your portfolio. So it's going to take time, but there is a trajectory that you can follow and reach this objective at some point. So it's doable. It's relatively easy to implement, and it's a kind of proof of concept that we wanted to do and say, okay, we can do this for stocks. So this is the equity portfolios that we're working with, but you can do the same thing for a bond portfolio or even for government bonds. So at the end of the day, if we manage to do this for a relatively well-defined portfolio, it could be applied to a complete portfolio. So data, I'm going to use data from TrueCost. So it's providing carbon emissions for all firms. I mean, a large number of firms. So if you look at the number for 2019, it's something like 15,000 firms. So it's quite a lot, and it's covering most of the production sector. We're looking at different scopes of emissions. So what we do in the analysis is we try to take the worst case scenario. So we take all the emissions emitted by the firm. So that's the direct emissions, the electricity, so the emission mix of the electricity you use, and also the emissions by firms that produced the product and services that you are using. And we make a comparison with a benchmark used by these firms, these funds, sorry, the asset managers. What we want to do is to see if we can decarbonize a portfolio without affecting too much the properties of the portfolio. If you affect too much the properties of the portfolio, they won't do this. And there is no discussion, I mean, there's no doubt about this. The portfolio managers, they will never go far from their benchmark. I mean, we would have to force them. So to show you why it's relatively easy to start with, here is a distribution. So we continue with factors and extreme values. That's the distribution of firms' carbon intensity. So this is the how many tons of CO2 equivalent you emit for 1 million of revenues. Okay, so just to produce 1 million of sales. This is the intensity that you need. So if you look at this number here, so the 7,500 number, that's the number of ton of CO2 equivalents that you need to produce for producing 1 million of sales. Okay, so this is a 1% threshold. So you have 1% of the firms that are polluting like crazy. Okay, the average is something like 300, so it's not that big. But if you look at these highly polluting firms, they are really polluting a lot. If you look at the scale, so that's a log scale. So just to make numbers comparable, so we start here on 100, but here we are at something like 10,000 tons. So by excluding a small number of firms, you're going to reduce a lot the carbon emissions of your portfolio. I'm going to take two measures to evaluate the impact of decarbonization on the portfolio. The first one is a weighted average carbon intensity. So we're just looking at the carbon intensity of firms, and we weight them to see what is the impact at the portfolio level of these carbon emissions. Okay, so it's just value weighted. So this is a weight of the firms into your portfolio, and you just take the average, weighted average. The second thing that is more interesting is what we call the carbon footprint. So the carbon footprint is how many tons of CO2 equivalent you emit for 1 million invested in your portfolio. Okay, so now the question is different because what we're looking at here is the ownership of the firm. So is of the fund. So, you know, what is the value, is a proportion of the assets of a company I own. Okay, so if I have a, let's say 1% share in the equity of a company, I'm contributing for 1% of its emission. Okay, so that's how we compute the carbon footprint. So that's a weighted average of the emissions, but weighted by the ownership of the company. So now just to define the rule and what we promote for asset managers, we rank the firms by their carbon intensity. We're going to exclude a given fraction of the value of the portfolio until we reach, let's say, 1% of the value of the portfolio. And then you're going to sell these shares, right? So you receive some proceeds. And the question is, what do we do with these proceeds? So the idea is to reinvest the proceeds into the same region and the same sector as the companies you have excluded. Okay, so doing this way, you keep the same risk exposures of your portfolio as the benchmark. Okay, so you are exposed to the same countries. So if you were invested in China, you sell shares from China, you reinvest in China. So you're going to be exposed to Chinese firms in the same way. You're going to be exposed in the same sectors. Okay, so you don't change the characteristics of your portfolio. Is it working? Actually, it's working pretty well, and it's working pretty well not by surprise. I mean, it's not by chance. It's just because of this highly asymmetric distribution of the carbon intensity, right? So you have extremely polluting firms. So if you just need to remove a few of them, and you're going to dramatically reduce the carbon footprint of your portfolio. Just to give you an example, this is the, just let me take this 90%. So I take the threshold at 90%, I exclude 10%. Okay, so I exclude 10% of the market value of the portfolio. And the carbon footprint is going to go down from 430 tons per million invested to 250 tons of CO2 per million invested. Okay, so by just excluding 10% of the firms, you reduce by almost 50% the carbon footprint of the portfolio. I don't want to lose time with the financials. Just one thing is it doesn't affect the performance of your portfolio. So you're going to generate the same performance, same return, same risk, and so on and so forth. So it has no impact on your portfolio. So this is one shot, right? So it's just for 1 year, you exclude 10% and you reduce by 40% the carbon footprint of your portfolio. The question, of course, is, okay, so you have done this once, but can you do it twice or 3 times or 4 times? So, you know, having a continuing decrease in the carbon footprint of your portfolio until you reach something like 0. That will be the key question. So what you can see here is how you can reduce the carbon footprint. So this is the carbon footprint of the portfolio. In black, you have the benchmark. In blue, you have when you exclude only 1%. In red, when you exclude 10% of the market value, and here in magenta, when you exclude 25%. What you can see is that you have to exclude more and more firms to have a similar impact as before. Okay, so here I just remove 9%, whereas here I just removed 1%. Okay, so you have decreasing returns if you want in the exclusion. Huh? So now this is the final step. How can we do this in a systematic way to fully decarbonize a portfolio? So we just took numbers from IPCC and see what is the carbon budget that is left, and how much should we reduce the carbon footprint every year to get a decarbonized portfolio that would be consistent with Paris Agreement. So essentially, we did some math from IPCC. So we took something like what is left as the carbon budget. It's not for only for firms, but it's just to give you an order of magnitude. So this is a carbon budget, 200 gigaton of CO2. Every year we emit something like 30 gigaton. So the decrease in the CO2 emissions should be something like 10% per year, but every year, right? So it's not just 1 year. It has to be every year you decrease the carbon emissions by 10%. So of course, we cannot look at the future. We don't know what will be the carbon emissions of companies in the future. They do some commitment, but it's not something we can verify for the time being. So what we did, we looked backward and we took data from 2010 to 2019. And so it makes 10 years. And we try to implement this strategy for 10 years and see, okay, can we do this? Is it costly? Is it something we can implement from a practical point of view? And in some sense, I mean, it's not the best case scenario. I mean, we should expect that in the future, the reduction in carbon emissions should go faster than in the last 10 years, right? I mean, if we go in the right direction, carbon emissions should reduce faster. So here it's...
Eric,
yes.
Just to be aware of the time.
Yeah, I'm aware, and this is essentially the almost the last table. I'm going to show you then one picture and I'm done. Yeah, so I took the 10% objective, okay, and I just would like to show you that this is something we can implement. So in 10 years, so we started in 2010, we go up to 2019, we reduce by almost 10% per year. And next year we do it again and again and again. So every year you have to reduce again. And you can obtain a cumulative reduction by almost 65% in 10 years. Right, so it's not fantastic, it's not exceptional. I mean, of course, I wish we could go to zero, but of course, we don't go to zero, but it's doable. Okay, so if just by excluding 10% every year of the worst polluting fields, what matters is what you can see. There are two things to finish. One is, this is the starting point here. So we start with a portfolio with that level of emissions. In blue, you have the benchmark. So the benchmark already decreased its emissions. So the average company has a decreasing level of emissions every year. Okay, there are some difficult years. So 2018, it increases, but on average, it decreases. And in black, you have the portfolio. Okay, so you can see that every year you exclude more and more firms, so the most polluting firms, and you reduce the emissions of your portfolio. And finally, this is the plot on at which level of pollution should you exclude firms. So here, the first year, you exclude all firms with a level of carbon intensity above 8,000 tons per $1 million of revenues. And the years after, it tells you what should be the threshold where you should exclude. And of course, at the end of the period, the level of exclusion is relatively low. So you have to exclude more and more firms. Okay, that's it. Just a last word. It's doable to decarbonize a portfolio. It's going to be relatively easy also because firms tend to reduce their carbon emissions over time. There may be some difficult years in the future. I mean, sometimes, for some reasons, carbon emissions tend to increase. So that was the case in 2018. If there is a decarbonization that is done on a relatively massive scale, it would have an impact on the cost of financing. So the most polluting firms should reduce their pollution just to be able to finance themselves. So it would have, a kind of virtuous cycle where, because you punish polluting firms, they will have to do something. They will have to clean their act. And of course, it's going to have an impact on actual emissions if it's done at a massive scale. So you need to have some coalition of asset managers willing to have an impact on society, and that's the way it would have to work. So I'm done. And I'm open to questions, of course. Thank you.
Thank you so much, Eric.